Okay, so let's consider this example. Let's say we have a linear program which looks pretty much similar to the previous ones, but now for the first constraint is actually greater than or equal to instead of less than or equal to. So in this particular case, we would not have a trivial basic feasible solution, okay? Because if you just get a very typical standard form, you don't have an identity matrix by free. So in that case, we would construct our phase 1 standard form linear program, okay? So we would add this artificial variable x5 after we do the standard form thing. Also, don't forget, we still always should first do those slack variables. We introduce those slack variables because they are meaningful. And then when we see we need some more variables to create the identity matrix we need, then we introduce artificial variables. Okay? So in this particular example, x3 and x4, they are slacks, and x5 is an artificial variable. So we introduce that x5, and then we get another linear program where we want to minimize x5, minimize the sum of all artificial variables. Okay? So don't forget, we need artificial variables because we need identity matrix. Because x4 already may serve as a part of the identity matrix, we only need one artificial variable. Okay, so let's take a look at this example. So pretty much what we try to do is to solve our previous example. Okay, so from this tableau, maybe you may also take a look and understand what we are trying to do. We want to maximize or minimize whatever subject to 2x1 plus x2 or x1 plus 2x2, okay, according to here, minus x3 plus x4. So we want to solve this particular linear system. Okay, so maybe we are given this formulation and we have no idea whether there is a feasible solution or not. Okay, then our strategy, as we mentioned, is to artificially add one variable called x5. Okay, if we do that, we say x5 is artificial. And we're going to see whether we may run some simplex iterations to take away this x5. So that's why we want to minimize x5 subject to all these things. So that's going to be translated into this formulation, into this tableau. So in this tableau, one thing to keep in mind is that, is this a valid tableau? No. Because we try to say x4 and x5 are our basic variables. But if that's the case, while there is an identity matrix here, your objective row are not all 0. Okay? So in that case, we need to adjust the zeroth row with elementary row operations. So we need to first do some adjustments. And the way to do it, of course, is to adjust row 0 by adding row 1 to row 0. So this is not a simplex iteration because we are not really doing pivoting. All we are doing is to make the two columns satisfying the conditions, the requirements for basic columns. Okay, so once we do that, now we are ready. We may take a look at those reduced costs. Okay, so the current basic feasible solution here 00066, which corresponds to an infeasible solution to the original LP. Why do we know it is infeasible? Because our artificial variable x5 is still positive. Somehow that means this 00 is not a feasible solution to the original problem, or this 0006 is not a basic feasible solution to the original standard form. Okay, so let's try to remove it. This guy is a minimization problem, so we need to look at positive reduced cost. So we enter x1. We do the ratio test, x5 should leave. So once we do that, we're done. We know x5 leave the basis. And there is a fact that whenever an artificial variable leaves the basis, we will not need to enter it again because there is no benefit at all. So we know if we want to save some time in doing handwriting calculations, we may remove that column. So that's why from the left to the right, after one iteration, one column disappears. The column for x5 for the artificial variable disappears. So we first find the entering column and the leaving column. We know x5 is leaving, so we take it away, we remove it. With the remaining 4 columns, we do all the usual pivoting. And then we're done. We're done with our new tableau. And in this way, the new tableau says that x1 and x4 should be our basis for the original problem. Okay? A feasible basis for the original problem would be x1 and x4. If you select that corresponding AB matrix, now the 2 columns is going to form an invertible matrix AB, and the AB inverse B is going to be non-negative. Actually, you also know that it's 3, 3. So now let's construct the phase 2 linear program. So first, if we are trying to maximize x1 plus x2, we may add that constraint objective function back by reverting their signs. So you are going to see -1 and -1 in your zeros row. So that makes sense. But also, this is the valid tableau. Again, it's not. Because column 1 here, ideally the number here should be 0. But now it's -1. So we need to fix the system again. So let's adjust the zeros row again. And here we are in the phase 2 LP. We need to first do adjustments to make this number 0 so that now we have a valid tableau where the basic columns are having identity at the constraint side, having zeros at the objective sides. So now all we need to do is the remaining very typical simplex method. We are solving a maximization problem, so this one enters, ratio test, these 2 will leave. And then we go to our second tableau. There is an entering variable, there is a leaving variable, and eventually we are done. Now we find an optimal basic feasible solution. We're going to see that x1 and x3 should be our basic variables. Their values should be 6 and 6, and that somehow gives us 6, 0, 6, 0 as our basic feasible solution. That is optimal. Again, we may graphically take a look at our search path. Originally, we start from x0 because originally our solution, our basic feasible solution is this one. If we exclude our artificial variable, then initially x0 is this one. This corresponds to the initial point here. And then we do one iteration to get to our initial basic feasible solution. As a result of phase 1 is this point. You are going to have x1 being 3 and x2 being 0 and some others. After 2 iterations, we then get to x3, which is optimal as a result of our phase 2 solution. So hopefully you would also go back to take a look at these tableaus, solutions, formulations again, and try to do all the things by yourselves. Go through all these examples so that you really know everything. Do the calculations. And pretty much that's the end for our discussions, introductions for the simplex method. So it may not be easy at the beginning because there are so many things to mention, but hopefully you get the idea. Pretty much we want to move along edges to find an extreme point solution. To do that with computers, we need to convert everything into algebra. So that's why we define standard form, basic feasible solutions, reduce cost, ratio test, so that we may iteratively find the entering variable, leaving variables. Sometimes we need to update the system to make the calculations easier. I hope you not just memorize these ideas. You may also appreciate the beauty under that. So the design itself is elegant. That's why it can be a classic algorithm. Okay, that's pretty much all I have at this moment. Thank you.